Um, Sorry, I need to. Yeah, so okay, maybe I cannot see your face, but just interrupt me at any time that you want to ask a question. Okay, so today I'm gonna talk about some recent work and tell you some story about the hydrodynamic effective field theory and the spontaneous symmetry breaking. Okay, so just a big outline of today's talk. I'm gonna first give an overview of the U1 SSB case and from different perspective using the EFT and also discuss the Ghosn theorem for that. And then I will mainly focus on the so-called strong to weak SSB for the U1 case and discuss it also from different perspective. And if time permits, I will say something about the SSB of the so-called Galilean boost symmetries. So first, the two parts is based on the work, the first paper that is below, and the third part is based on the second work listed below. So I would first um, acknowledge my collaborators during these projects. And also thanks, I think during the time when I was at KITP, I had many interesting and useful discussions with many of you in the audience. Yeah. Okay, so let me just start with some big picture about what is hydrodynamics. So when we say hydrodynamics, the first thing that comes into my mind is so-called Navier-Stokes equation, which describes how fluid will flow. And also there might be some process which doesn't involve the fluid elements, but it involves some particles and the diffusive process of that is also sort of a subfield of hydrodynamics. Well, this is classical, but there are many recent progress of using the idea of hydrodynamics to apply it to dynamics in quantum antibody systems. So for example, if you have a Fermi liquid where your electrons will flow collectively, and suppose your Fermi liquid is clean enough and there's no disorder, you may expect that momentum would be a good conserved quantity and will drive you like some fluid dynamics. But unfortunately, many materials will still relax its momentum due to so-called Clap scatterings. But people realize, so, for example, if you have a small enough Fermi surface, this kind of process can be surprised. And then you do have a well-defined conservation law for the momentum. And then electrons will indeed flow like a fluid at late time in experiments. So here are some theory work that done with respect to this kind of hydrodynamic flow motion in certain condensed matter materials. For example, the first setup is a narrow channel where you can insert a jet of current from the top and drive it to the bottom. In the disorder case, the flow would just be some kind of a sort of like a unidirection flow, while in the hydrodynamic, because of certain non-locality that happens in the hydrodynamic region, you will see that vortices will develop during this process. And another setup using very similar idea of using this kind of spatially resolved transport is not to make a channel, but make a constriction with an opening at the center. So if you inject a current flow through this device, the current can only come through the center. But in the hydrodynamics region, the conductivity of your current will surprise at large momentum. This means that near the corner of your opening, like the corner of your constriction, the flow will be surprised, while at the center, because of the current conservation, you still expect more current flow at the center than the one near the corner. So showing in the bottom is a comparison between the physics region where you have the hydrodynamic behavior and the ballistic region where you basically have a single particle picture of that flow. Another interesting experiment, actually, I think this is the like a very striking observation that stimulate many discussions and progress recently about this hydrodynamic behavior in quantum antibody systems. So people look at the graphene where the sample is really clean and near the Dirac point where you can basically neglect the Wouldclimb scattering. However, the Dirac point is a little bit different from the Fermi liquid because it's sort of similar to so-called quantum criticality where, and in the Dirac point, you will basically break the Gaussian invariance, which is maintained in the Fermi liquid region. So in any case, what the people find is that the Lorentz ratio, which is typically defined as the thermal conductivity over the electric conductivity, has some huge peak near the Dirac point. So this is really due to the fact that conventionally the thermal conductivity and the electric conductivity has the same origin of relaxation. But now in the Dirac point, they can have different mechanisms due to the lack of the Gaussian invariance. So basically the current may not be carried by the momentum in that case. So people have predicted this behavior using hydrodynamic theory, and people have found this really striking experimental evidence to support that really we can talk about hydrodynamics in quantum antibody systems. Okay. So now I would like to focus on the low energy mode about your hydrodynamics theory. So within linear response, if you have a conserved U1 charge and imagine that you put a bunch of particles at one place and let it evolve. So the typical evolution will be captured by so-called diffusion, where the low energy mode is given by the first line, which is quadratic in momentum for its flow, and it comes as a minus imaginary part of your frequency. But for Navier-Stokes equation, you also have fluid-like motions. So imagine that you have a fluid instead of only have a U1 charge. You can now imagine to compress your fluid. So this compressibility can drive you certain so-called sound wave in your hydrodynamic theory. And this sound wave is really like a propagating wave that can carry energy ballistically, while in the front of it still have some diffusive behavior. However, this is only happening in the longitudinal sense, not the shear sense, because if you shear your fluid, you can imagine that there should nothing be happen for at very leading order. So there's only the sound mode in the longitudinal direction. Well, recently people have thought about certain generalization of this kind of hydrodynamic behavior. So essentially, people are curious about the case where it's not only the diffusion, but maybe develop some sub-diffusive behavior, meaning that the particles, the collective behavior is way slower than what you would expect. So one of the example is to impose so-called dipole symmetry, where you basically forbid single particles motion, but allow, for example, the center of mass of your particle hole pair to move. So with this additional symmetry, you will get a sub-diffusive behavior with the dynamic exponent z from 2 to go to 4. And correspondingly, if you add momentum conservation to these systems, but together with the dipole symmetry, because of the slow motion, the propagating mode will also be slower than you would expect. So in this sense, we see many low-lying gapless mode that happening during in this hydrodynamic region. So one interesting observation is that this gapless mode is actually protected by the symmetries that we impose. For example, if you have additional dipole constraint symmetry, you will get different behavior of your phase of matter. So let me just make some analogy between the equilibrium phase that people are familiar with against this non-equilibrium phase of matter, where you can imagine the linear response theory is like the mean field level, and some dynamical fluctuations can correspond to some quantum fluctuation that happens in your equilibrium phase. So one example is so-called KBZ class, where instead of get diffusion, there are some instabilities that can happen in, for example, one-dimensional fluid dynamic that drive you to some super diffusive behavior. And more recently, we have generate this concept into higher dimension using this dipole constraint. Okay, so the reason that I want to bring this up is because recently we also realized that this higher dimensional generalization of the KPZ class, especially in 2-dimension, can potentially be actually realized in so-called quantum Hall crystal regions. I think there's a lot of interest happening in Cornell about the quantum Hall and anomalous quantum Hall effect. So I would like to see if there's any chance to observe this in real experiment. But for today's talk, I will focus on the linear response region and not talk about these kind of fluctuations. Okay, so having talked about this hydrodynamic mode, we know from our experience that gapless phase, there has to be some mechanism to protect this gaplessness. So examples include, for example, the symmetry anomaly. So imagine you have a quantum Hall state, you have a chiral edge mode, and the chiral edge mode is gapless. And the gapless, in the sense, there's a chiral anomaly happening there. Also, this chiral anomaly can be generalized to higher dimension in all dimension. For example, the well-set metal, you also get this gapless mode. Another mechanism is that you can break your continuous symmetry spontaneously, where you get Nambu-Gostan mode that support these gapless excitations. So the question is that is there any mechanism
I have a quick question. So yeah. What about just Fermi liquid that's gapless?
Okay, so Fermi liquid is a little bit subtle. So like there are some, like at least there are two modern ways of framing it. So one is use so-called loop U1 symmetry by MIT group, and the other one is so-called co-adjoint orbit method by just framing this as Hamiltonian dynamics that happening on the phase space that has equilibrium state given by the Fermi surface. So indeed, you can get this linear Fermi liquid behavior by treating this loop U1 symmetry as a global symmetry, which we had to work on that. But there are some subtleties regarding whether or not this nonlinear terms is important. So the basic, so I think the bottom line is that the more correct way of framing at least this Fermi liquid, let's not talk about non-Fermi liquid, is to use the co-adjoint orbit method. But I guess this is a little bit different from what I'm talking about today, because you can imagine on the Fermi series, there are even many degree of freedoms. But today I got to focus on the finite number concern.
Maybe let me ask you in a different way. So the way you're phrasing things makes it sound like gaplessness is very special. Right, that you need something protected.
Yeah,
right? That's just
I think gapless is special. Yeah.
So you have this picture that a generic system is gapped, and maybe it's coming from different places, but that's not obvious to me. Maybe someone else can.
Okay, so I will mention. So indeed, there's some work suggesting that Fermi liquid can also think about as SSB phase, but not in a conventional sense, but in the sense like the Gaussian boost is spontaneously broken. So I will talk about that later. Yeah.
Does that require you to have a spherical Fermi surface or generic Fermi surface?
Sorry.
So
Maybe generic Fermi surface. So
now,
well, I'm not talking about some singularity that happening. So I'm just talking about some universal features that, I mean, Landau would predict, for example.
And it's part of the heuristics that this is just heuristics.
Yeah, please.
If you have a gap that's not at a point, but an entire face,
Yeah.
means that you could change your parameter and the gapless stuff is still always there for some reason. And naively, if you have a lot of gapless degrees of freedom, you can turn on interactions and try to remove them to the best ability you can. And there must be some kind of a weird stuff going on that doesn't allow you to do that. I guess this is where he's kind of
Right. So I guess, if I have, and there's probably some assumption going on here that I'm not aware of, right? But if I think about a ferromagnet, right? I guess that is a spontaneous theory.
Yeah, exactly.
But so a paramagnet.
Paramagnet is usually gapped.
It's usually gapped.
Yeah.
The
disorder phase, like short range correlation, everything indicates eventually.
Yeah, I think but so if I heat up a piece, right? So there's some assumption of zero temperature and
So I will talk about the heating. It's essentially, I guess. So okay, so part of the like say you have an insulator and you heat it up. What you get? Maybe, I mean, you can still argue there's still gap, but maybe at a dissipative level you can have a diffusion mode. Right. So I'm trying to provide a perspective at least to talk about certain gaplessness that happens in the hydrodynamic region. Just trying to make analogy with what people talk about equilibrium phase, but for sure, I mean, there's a lot of things to do, like to really pin down the phase of matter at non-equilibrium. So I would just say like, we can definitely chat more about that later. But
thank you.
That's for the question. Yes, I guess, again, I just want to provide a perspective about how to think about this hydro mode. Try my best to think about it in terms of the conventional language and to see whether there's something interesting that can happen. Maybe this is a way to think about the interesting thing. Yeah, anyway. Right, so let me just let me just briefly mention the idea of the effective field theory that I'm gonna use. So basically, the idea of effective field theory is to focus on the low energy degree of freedoms in order to characterize these low energy excitations. A canonical example is, say you have a U1 conservation, you have U1 charge. So by Noether's theorem, you get a conserved current, and you have the charge conservation law given by this equation. And so to get a response from this theory, you usually just couple it to some background gauge field. Here is the U1 gauge field. However, this theory is still too complicated, and you can imagine if you have a Fermi-Haber model with U1 conservation, you still don't know how to solve it. But the idea of the effective field theory is to say that imagine that we can integrate out this, like the irrelevant degree of freedom, and just focusing on the low energy subspace, then you can deduce the effective action as an action that obeys all the symmetries. For example, here I'm introducing low energy degree of freedom to make sure that the gauge invariance is captured by this effective action. And then we need to ask whether this symmetry has an anomaly or whether this is symmetry is SSB or not. Based on that, we can give additional constraint on the effective action. And the next step is to do a derivative expansion of the building blocks that you have in the sense that at the long wavelengths and the late time limit. So if you want to build a non-equilibrium EFT, you need to put the series what I described above on the string-Keldysh formulation as the standard formulation to describe non-equilibrium systems. Right. Okay. So to give you a sense of the effective field theory, let me start with the conventional superfluid phase where the U1 symmetry is SSB. So here I'm showing you a very general definition, for example, about SSB, where you basically have a state that transform non-trivially under your symmetry group, while your Hamiltonian, which captures your dynamics, is symmetric. So this condition implies that if you want to probe a system with some like charged observable, which by charge I mean it changes under conjugation by your unitary transformations of your group, then you can deduce that the following quantities is not zero because your state breaks the symmetries. So a concrete example, let's take the symmetry to be U1, and now the symmetry generator becomes the total charge of your systems. And the condition that a charge observable will observe this state becomes that the charge under a small symmetry twist of your charge observable, you get a non-vanishing expectation value on your state. So a canonical choice of this charge observable is the phase variables. And because the phase variables form a canonical conjugate pair with your charge density, you will see that this condition of SSB will imply that A is really the order parameter. So this is just a recap of the textbook formula of the U1 SSB. So now let's see. Let's take the phi field. Now, let's not exponentially, but just take it as a low energy degree of freedom. So one caveat is that phi field should be compact, like it has to be the same value plus 2 pi of it. But so just for our purpose and to just describe the low energy theory that deep into the superfluid phase, we can just neglect that fact. But if you want to be careful about the transition, you need to take that back. So the fact that this phi field acquires the expectation value as an order parameter, meaning that there is a freedom to choose the reference point or maybe the boundary condition by just adding some arbitrary numbers to the phase so that the theory doesn't change. So recall that we have the canonical pair between the phase variables and charge density. We can write down a Lagrangian field theory just as the classical field theory textbook would do. So the first term would just capture their two canonical conjugate pair, and you add a Hamiltonian by hand. But the Hamiltonian, recall that there's a shift symmetry of your phi field. So the Hamiltonian can only depend on the gradient of phi field, because otherwise the theory would not be invariant on this shift symmetry. So the most general form of the Hamiltonian would be in the leading order of derivative expansion is that you have the energy density term plus some gradient of your phase field. So now if you integrate out the charge density, you will get the constraint that dt phi would be given by the chemical potential, which is related to the charge density by this thermodynamic relation. And the later step is to expand around this background and rewrite your effective Lagrangian field theory in terms of the new fluctuation phi tilde field. And indeed, you get the Navier-Stokes mode at the end of the day. By just calculating the equation of motion for that. Okay, so after talking about EFT perspective, there's also a perspective from so-called Goldstone theorem. So given the fact that the phi field and charge density is a canonical conjugate pair, you can calculate the retarded Green's function using these two variables. And because of the condition that is SSB, this term would not vanish. And if you do a Fourier transform, you'll see that the imaginary part of the retarded Green's function, which is a spectral weight, have a support which suggests that at zero momentum, and there will be a single particle excitation that causes zero energy, which implies which is really a condition of a gapless excitations. So what Ghosn's theorem says is that if you have a continuous SSB, it implies a gapless single particle excitations. Okay, so before I talking about the non-equilibrium dynamics, is there any questions regarding the setup? Okay. Okay, so I would like to move on to talk about the non-equilibrium dynamics. So first, I would like to introduce a concept that people talk about today. It's so-called symmetries in the quantum mixed state. So in the mixed state, you have densities. You have a density operator instead of your pure state. So there are two ways of acting the unity transformations. If you only act on one side, it gives you a so-called strong symmetry. Well, if you conjugate it on two sides, it means it corresponds to so-called weak symmetries. So the example is, for example, at even temperature, you have the density matrix given by the identity operator, which is weakly symmetric because whenever there's a non-trivial unitary operator acting on it, it will change the state. Another example of the strongly symmetric state is the following state. It's like if you have a Z2 symmetry, like IC model, the symmetric state would be something like 1 plus X, which doesn't change if you X the symmetry on one side. So this idea can also be applied to define so-called strongly symmetric dynamics and also weakly symmetric dynamics. Example is that if you just have your Hamiltonian dynamics, which gives you the unitary dynamics, that dynamics is strongly symmetric because your Hamiltonian, by assumption, is symmetric under the symmetry group, will just commute with the unitary operator on each side. Well, there's some possibilities to have weakly symmetric dynamics if you have a more general open quantum systems. Like you can include a Lindblad operator such that it only commute with the unitary operator on both sides together. So this kind of application of symmetry will provide a new avenue about the phase transitions. And in particular, it will suggest a new phase transitions between the so-called strong symmetry, from the strong symmetry to the weak symmetry. And this is recently proposed as so-called strong to weak SSB. Okay, so I think the discussion about this strong to weak SSB starts early this year and about discrete symmetries. So I don't have energies to list all the papers that talk about this, but so forgive me, I didn't list your work, but I do a search about it on arXiv just with the title that include these keywords, including the strong weak symmetry breaking. And in the past 6 months, there are like 12 papers that talking about this. It's like on average, there's like 2 papers each month that talking about it. So it's really, you can see that it's really a interesting topic and people get interested in that, and very many efforts has been put into this field. So, well, the 2 pioneer papers had an outlook section that both talk about the possible directions about the continuous symmetries, like what happens if you have a continuous symmetry that is strong to weak SSB. So we know that for weak SSB, it just gives you what I described before as the superfluid phase. But it seems to be a puzzling fact that if you have a strong U1 symmetry, do you get 2 superfluid phases or something else? Well, so in the later slides, I gotta try to convince you that it's not actually 2 Ghosn mode, but the Ghosn mode for the strong to weak SSB is the so-called diffusion mode that happens in hydrodynamic region. Okay. Right. So actually, it's convenient to just start by generalizing the pure state U1. Sorry, is that a question?
No.
Okay. Okay, sorry. It's convenient to start with a generalized ghost theorem that generalizes the version of the pure state U1 symmetry to the mixed state. So now the claim is that the strong symmetry twist, you still need to find some twist of your a charge operator under the symmetry. But now the strong symmetry twist is not given by the commutator, but given by the anti-commutator. So you can imagine this by thinking about the fact that you have a commutator because the weak symmetry acts conjugately to your charge operator so that you get a commutator by expanding this out. But now if you have a strong symmetry, you are allowed to act it similarly on two sides. But because of the claim that it doesn't change the operator if you act it on the one side, so if you act on two sides, it still doesn't change. So if you expand this kind of operations to leading order, what you get is anti-commutation. And now like we also want to talk about the expectation value with respect to certain state, and it turns out the way that we're gonna frame it is to think about this happens in so-called thermal equilibrium, or more generally the steady state, to talk about a strong weak SSB. Okay, let me just take an example for the U1 as strong weak SSB. So let's just take the charge operator to be the charge density, and then if you plug it into what we claim as a definition of your strong weak SSB, you will see that the expression will exactly be given by so-called charge susceptibility. Now, if you do a Fourier transformation, you will see that the symmetric Green's function will get a peak at zero momentum, zero frequency, provided that your charge susceptibility is non-zero. So I will later show you that this symmetric Green's function can actually be related to the spectral weight in the double Hilbert space using the fluctuation dissipation theorems. But for now, let's just look at this expression. So you see that the fact that there is the twist the twist of your operator still get the expectation value of your thermal equilibrium. It's really reflected to the fact that your charge can really fluctuate locally, and this ability is captured by the so-called charge susceptibility. And so this means that charge susceptibility is really the order parameters of your strong to weak SSB. So an example of the fact that there's no strong to weak SSB is when the charge susceptibility is zero. For example, if you have an atomic insulator, the charge are pinned at every site, then this charge susceptibility would be exactly zero, and the atomic insulator will be a good state that doesn't break your strong symmetries, because on every side the charge is fixed. So you can imagine that total charge is just fixed to certain numbers and doesn't fluctuate. Okay. Right. So as I mentioned, this non-zero charge susceptibility is all the parameter for strong weak SSB. So another way to say this is that this charge susceptibility is really means that you have the ability to have the ground canonical ensemble as the steady state of your dynamics. So a ground canonical ensemble is a state that will, by definition will exchange particles with so-called environment. So that means that the ground canonical ensemble can never be a state that is strongly symmetric because of the fact that it will couple to the environment. However, it is still weakly symmetric. So this really this fits to the definition that strong weak SSB, like we start with the evolution that is strongly symmetric, but the state the steady state that you talk about is not invariant of strong symmetry, but invariant of weak symmetry.
Question.
Yeah.
So if I have an Anderson insulator, you call it by this metric, you would call it symmetry broken.
Anderson insulator.
Yeah, like
Um,
the spectrum is completely dense, but it's
Yeah.
a piece of insulator. So, as far as electrical transport goes.
So I think sorry.
Yeah, and then it should have a finite compressibility. Just like a metal.
Yeah. Okay. So I guess the reason I mentioned is the atomic insulator is I want to avoid some thermally excitation. So for generic insulators, you can still have diffusion. But only in the extreme limit where the charge sensitivity is not zero, that you cannot have diffusion. So in that sense, I think the Anderson insulator is also an example of that.
So sorry, why is diffusion in part of this story? Because I thought we were just defining what. I think.
Oh, so I guess I will show you that diffusion is Gaussian mode for this strong to weak SSB of U1 symmetry.
Meaning that, okay, so I guess if I don't want to jump ahead, and you will tell me Anderson insulator is a U1 SSB, and then you will later tell me that an Anderson insulator will have a diffusion mode in it. Is that what's going to happen? Or
yeah.
Okay.
Good. Okay. Yeah, I guess. Okay. So regarding this point, I guess what I mentioned here is really a definition regarding charge susceptibility, where it's not really care about the microscopic realization of that. So I think as soon as there's a charge susceptibility, you get this strong to weak SSB phenomenon. Yeah. All right. So before, let's just take an analogy with the U1 SSB case. So imagine that at U1 you have a massing head and you can rotate the state by your symmetry operators. But now, what does rotation means for the strong weak SSB is to actually shift your chemical potential by acting the charge by acting the symmetry on that. So but chemical potential can be arbitrary number. It can be on a real number. So this kind of rotation is not a compact operation, but it's really acting on a real line. So in that sense, you can see that originally there are so-called Mermin-Wagner theorem that forbids the IR fluctuations of the Gaussian modes for continuous symmetry at finite temperature in dimension 2. But here, the difference is that the degenerate manifold is not compact, but it's a real line. So the Mermin-Wagner theorem no longer applies to that case. Okay, so yeah, let's try to make a concrete example about this strong to weak SSB. So the starting point is to frame this pure state in a W Hilbert space. So this is just making the bracket structure as a single bra structure, but in the sense of the W Hilbert space. And you can define the left and right operators that acting originally on the bra and the cat to acting on the double Hilbert space as well. So the model that I'm gonna talk about is so-called quantum rotor model, where you have the again phase degree of freedom and the charge density degree of freedom on each side, and they form a canonical conjugate pair. And we are interested in a thermal your steady state that is characterized by a function phi that is a function of your charge density, and this basically just represents a different charge assignment to different charge sectors of your final density state. So you can show that this state is not it actually breaks the left and the right U1 symmetries, but it preserves the diagonal part of this U1 cross U1 group symmetry. So accordingly, what it means is that if we define so-called strong charge as the QA operator and the weak charge of QR operator, if you add QR on the state doesn't change. Well, if you add QA on the state will shift, the phi function would shift. I guess let me take a brief detour to talk about the long-range order that has been talked about by people in the literature about this strong to weak SSB. So in analogy to the pure state SSB, the ground canonical ensemble is really the ferromagnetic state for the Z2 SSB case, but the canonical ensemble is more like the superpositions of the two degenerate ground states in the Z2 SSB case. So we are mostly interested in the ground canonical ensemble, but you can ask why that is SSB. So we show that the condition to say that this is SSB is to find that the corresponding superposition of your ensemble, which now becomes a canonical ensemble, is actually have a long range order in 2-point correlation functions. But here it's a little bit special because you are talking about double Hilbert space. So there is a new correlation function that can capture this effect. So this correlation function is so-called fidelity correlation, and it's defined in these two papers. What I'm gonna just briefly mention is like here, the rho tilde is the canonical ensemble that we can construct out of the ground canonical ensemble by just picking the total charge to be some fixed number. And we can calculate the fidelity correlation and show that it has a non-vanishing decay, which represents the long range order. And exactly, it's only when the phi function, which characterizes the distribution of a charge density, is a delta function, then it represents that there's no chemical potential you can do. And this represents certain, for example, the atomic insulator case. And in that case, because AP is 0, there's no long range order, and you cannot talk about the strong weak SSB. So the point is that the Murphy-Weinberg theorem can also be seen from this perspective by saying that AP is not a function of the distance. So it's always hold. Okay, so this is just a detour. So I want to mention to avoid the confusions that might happen during this talk. So after constructing this steady state, I want to construct a phase field that basically mimicking the phase field that we talk about in the U1 case. So this phase field defined in the double Hilbert space can also be think about as the Keldysh fields in the Schwinger-Keldysh formation. But just to summarize this page, the convenient way to see the relation between the charge and the phase field is to see that the phi field, which is conventionally called quantum field in Schwinger-Keldysh formation, is a canonical conjugate pair to the strong symmetry that we define here. And the classical field is the canonical conjugate pair to the weak symmetry that we define here. So essentially, if you apply e to the I phi a, that will increase your strong symmetry charge, and also corresponding, the phi r will increase the weak symmetry charge. Okay, because we're talking about thermal equilibrium, there are additional very important symmetries that we need to keep track of. And this is exactly because these symmetries that it will give you a different structure as the pure state SSB phase. So the symmetry can be seen as the following. So if you just, on the left-hand side is a single copy Hilbert space identity. And if you phrase it into the double Hilbert space, we can define so-called operation by operation called tilde, where you just change your original operator A to A tilde by conjugate the S operator, which is defined on the slide, and also take the dagger of that. So the claim is that after you doing this generalized time reversal symmetry, if suppose originally A is the dynamics that that guarantees that you approach a steady state, then A tilde is also dynamics. And at the same time, it will also approach the same steady state. So in this sense, A tilde is a time reversal parameter of A. And you can see that if you apply the tilde operator twice, you will get back your original A operator. So if we apply this time reversal symmetry to the variable that we defined in the previous slides, we'll get the following. And here I'm defining the chemical potential to just be the fact that if you slightly twist your the function phi, you will get increase of your chemical potential. So the important fact is that the non-trivial transformation is really the quantum phi A field, where it under this generous time reversal, you will acquire additional term that is proportional to the chemical potential. So this symmetry is actually not quite exotic because it actually happens in thermal equilibrium. It's known as the Kubo-Martin-Schringer symmetry. And there is a lot of works that showing that this symmetry is actually very powerful, and it implies that many like relation that should hold in Landau's paradigm, for example, the fluctuation dissipation theorem, the Onsager relation, and also the second law of thermodynamics, meaning that the entropy current is the entropy rate is non-negative. Okay, so given what I described before, let me just summarize what kind of symmetries and kind of effective field theory that we can build with. So recall that the quantum phi A field is a canonical conjugate pair of the strong charge, which is Na here, and the phi R field is the canonical conjugate pair of the weak symmetry here. So you can basically generalize what we see with the U1 case to this mixed state case with two conjugate pair, and together with the H tilde that describes generically the dynamics on this double Hilbert space. So there are several constraints, and that happens to constrain the form of the H tilde in the above Lindblad. So I'm gonna just go through these symmetries, but not showing you how to really derive the H tilde and just show you the final results. But I guess it's an easy practice to just check that indeed the final effective field theory is invariant on that. Okay, so first we have this generalized time reversal symmetry that non-trivially will shape the quantum field phi A by the chemical potential. And here I'm using the long wavelength limit by approximating the chemical potential to be the thermodynamic variables that obey the equation of state that we learned from the statistics field theory class. Okay, so the second symmetry that we impose, so recall that in the U1 symmetry, U1 pure state case, we have this shape symmetry because the phi field that we have in the U1 case is spontaneously broken, characterized spontaneous broken phase, so you are allowed to shift it. So here, what is broken is the strong symmetry, so you are allowed to shift the quantum field phi A by a constant number. However, the weak symmetry is not broken, so we don't have this freedom to shift the weak symmetry. Instead, we need to guarantee that there's no fluctuations happening in the weak symmetry side, which concerns the so-called classical field in the string cottage formation. And this tells you that this phi R field should be able to shift by an arbitrary spatial function, and that doesn't change the action. And in fact, what this means that you cannot have gradient of phi R in your action because that still changes under this symmetry. So this suggests that the phi R field is really sort of fixed in the sense in the space, and it cannot not have fluctuations. Rather, rather than a ghost mode, which considers the fluctuations of your phase field. The third symmetry that we have is just to make sure that your path integral is well defined, so that the imaginary part of your tilde h is negative. Well, the fact that the tilde h has the imaginary part is really tells you that there's some dissipative effect happening in the double Hilbert space. So the final point is to say that under the dynamics of the H tilde, you still have the trace preserving property of your density matrix. So this means that if you apply a strong symmetry charge, that is like an anti-commutator of your operator between your density matrix and the operator, but that would not give you will not guarantee that dynamics is conserved. Dynamics has a trace one that under the density matrix has a trace one under this dynamics. And similarly, applying a phi r field would tells you that you shift this left and the right charge differently, and that also breaks these trace preserving properties. So in short, these are the symmetry that you can find, and what you will get is that the most generic dynamics of your H tilde can be written as the following. So the first term can be similarly compared to so-called energy density in the previous energy density in the pure state U1 SSB case. And the second term is about the ghost mode. And you can see that the quadratic term in phi A field is the right phi A square. But because of the generalized time reversal symmetry, you need to shift one of the phi A by the chemical potential to make sure that all of terms are invariant on this generalized time reversal symmetry. And because of this shift, it will give you a diffusion mode, as we'll see in the next slide. Okay, just a brief comment that this formulation allows you to have the mu hat to not be given by the chemical potential. So this means that there's some chance for your dynamics to not given by your Hamiltonian. There's some chance for your steady state to not given by the Hamiltonian, which generates your dynamics. But I guess I won't have time to talk too much along that line. So it's just a brief remark for this purpose. Okay, so if you doing the similar integration as we do for the U1 SSB case by integrate out the NR field, you'll get the final effective action just in terms of the A field. And upon variation of phi A, you get the diffusion equation. And by just Fourier transform, you will get the diffusive normal modes. Okay, so now let's take the in the sense in the double Hilbert space as the phase field of phi A, and calculate the retarded Green's function in just follow the definition of it and calculate the imaginary part. So fluctuated dissipation theorem will tell you that it's related to the symmetric Green's function by the following structure. I recall that we have seen that the symmetric Green's function has a peak, provided that you have a non-zero charge susceptibility at a zero momentum, zero frequency. That means this newly defined spectral weight on the W Hilbert space will also have this zero momentum, zero frequency support. And this suggests there is gapless excitations that could happen in W Hilbert space. And this completes what we call about the generalized Ghosn theorem. Okay. Yeah.
Is it fair to say that the claim here is that the diffusion mode is the Ghosn mode? Here?
Yes.
If so, then let me make a comparison. In normal symmetry breaking situation, if you go into the spontaneous symmetry broken phase and then you explicitly break it by hand, you will turn a Ghosn mode into a pseudo Ghosn mode, make it gapped. Right.
Mm-hmm.
So now.
Right. So here, yeah. So go ahead.
Yeah, I'm just saying, okay, like I can switch from, I don't know, a canonical ensemble to a grand canonical ensemble at any time I want. That's the analogy of breaking the strong charge symmetry by hand. But is that gonna kill the diffusion mode according to that?
Oh, okay. So that's a different point, I guess. So that you end up having the ground canonical ensemble at thermodynamic limit is very similar to the fact that you won't have cat state, really won't have cat state in thermodynamic limit because the time will be exponentially long time. So you end up having the ground state is really the ferromagnetic ground state, which breaks your Z2 symmetries. So similarly here, what happens is like you really end up having the ground, yeah.
Sorry to interrupt, but with Z2, there's no ghost of mode, so I don't think that's a fair comparison.
Yeah, there's no ghost, but I'm trying to say that the analogy carries over. Like you end up in the thermodynamic limit, you still get this ground canonical ensemble as the. Another way of putting this is that if you have a canonical ensemble, like in the U1 case, you will see that you get a superposition of different points on the Mexican head. But that is not a convenient starting point to study the ghost mode because the ghost mode is really a low energy excitation at certain fluctuations of your order parameters. And if you superimpose them to make sure that the state is symmetric, that in that case, the ghost mode will not manifest as the low energy excitations. So similarly here, what we're trying to show is that we just concern about the ground ensemble and see the small fluctuations regarding the local charge density and see that this corresponds to the diffusion, which is the ghost mode of the strong to weak SSB.
This may take a longer discussion, but I want to point out that the Mexican head analogy is missing something. If I break the symmetry by hand, the Mexican head is tilted. The ghostal mode will
okay. No
longer be a true ghostal mode, so it becomes massive when you tilt the Mexican head.
Okay, I see. Right, sorry. So if you want to get massive, you can also do it in this effective field theory. You just by adding the phi A quadratic term to that equation. So without grad, you get phi A quadratic, but you also need to make sure that general temperature symmetry is preserved. So you get a non-grad term with the chemical potential, which will give you the gap for your diffusing mode. So that is an analogy I think would answer the questions.
So it's m minus idk squared instead of idk squared.
Sorry. So here the k square is because you have two gradients in the effective action. Now, if you allow the symmetry to be broken explicitly, then you don't have the shape symmetry. Then you are allowed to add the phi A quadratic term without gradient, and that term will give you something that non-vanishing if you take k go to 0. So that is what I'm saying. Like if you have the strong symmetry to be explicitly broken, your diffusion mode will also acquire a gap in that sense.
Right, but you could just break it by going to the canonical ensemble, grand canonical ensemble.
No, but sorry. So in the ground canonical ensemble, you still have the ability to square as strong to weak as a speed phase, right? It's not every.
I thought when I choose to do grand canonical ensemble, the symmetry is broken explicitly by hand.
No, it could be broken explicitly, but it could also be broken spontaneously.
Okay, maybe.
Yeah.
I don't want to hold you here for too long. So,
yeah. Thanks. I guess. Yeah. I mean, I agree that this is a subtle point that if you start with a ground ensemble, you cannot tell whether it's spontaneously or explicitly broken. So that's why I'm taking a detour to trying to talk about the long range order, etc. But yeah, let's keep discussing later about this point. Okay, so now we have seen that. So in fact, U1 char diffusion picture can be carried over to the other diffusive behavior in hydrodynamic mode. For example,
just a quick comment. I hope you're just about finishing up because we're almost out of time.
Yeah, I'm about finished. It's just 2 slides.
Sure. Okay. Thanks.
Yeah. Great. Okay, so can be carried over to the sound mode diffusive behavior as well. But there is also additional mode that in the sound mode that is not dissipated, but is propagating. So what about it, and what happened to that mode? So there are a lot. There actually works that showing that this sound mode actually saturate the Goldstone theorem for Lorentz boost symmetries in conformal field theory and also in Fermi liquid. So they basically show that low energy sound mode would be the candidate of your Lorentz boost SSB. This picture can also be carried over to non-relativity theory with a Gaussian boost. And on the left-hand side, I'm just showing you the boost symmetry algebra, where the Ki is the Gaussian boost. And what it tells you is actually a well-known effect that your hydrodynamic theory is the same in different inertial frame. And this is basically saying that momentum density will transform on the Gaussian boost. And because this nonlinear realize these symmetries, we would say that momentum density is all the parameter of that. So, but there's still some puzzling about this is that what happened, like, so why is what exactly is the Goldstone mode of a Gaussian boost? What we show is that suppose we just honestly treat every symmetry at face value and write down the cosine construction that we do for every spontaneous symmetry breaking phase, but here is for the space-time case. What we can see is that for the boost world identity at the ideal level without dissipation, the Goldstone mode here for the boost symmetry is the eta. And eta would be approximately given by the velocity field of your theory. And moreover, we give a stronger statement about this is that once you include dissipations, you will see that the fact that the Gaussian boost doesn't commute with your Hamiltonian will give you a finite relaxation time for your eta field. So that means eta field is no longer a good low energy mode anymore in the hydrodynamic regime. And that tells you that the velocity field is really the Goldstone mode for your Gaussian boost symmetry. Okay, so I guess I will just end out here, and to quickly summarize the main result is that I hope to provide a perspective about this gapless mode in hydrodynamic region from a conventional Landau's way of saying that they are coming from the strong two-weak symmetry. Spontaneous symmetry breaking mechanism. And there's a lot of interesting potential questions that we can ask. For example, in pure state, we know there are like type 1 and type 2 Goldstone mode that we can classify regarding the symmetries that we have. And there is possibly a similar classification that we can talk about the Goldstone for this strong to weak SSB as well. So, and with that, I would like to thank you for your attention, and I'm happy to take questions.
Thank you very much. We had quite a few questions, but if there are any pressing ones, urgent questions. All right. Well, in this case, thank you very much for your talk.
Thanks a lot.
Yeah, thanks.